Hello students, I hope all of you are doing well in this current critical situation of COVID-19 and also the super cyclone of Amphan has really hampered our life, but we have resumed our online teaching and learning session. So we are going to discuss about formal language and automata theory. In automata theory, so far we have discussed until the uh, in the last lecture we have discussed about the regular expression also, and also the different topics about the NFA and DFA. But we are going to discuss about the regular expression and pumping lemma. So let's begin our lecture. So today we are going to discuss miscellaneous topics related to the regular expression. Then we are going to the pumping lemma, and finally, if possible, we will try to introduce the basics of regular grammar and regular language, and we will see how regular expression comes into it. Okay. So first of all, we need to discuss or remember these identities of regular expression. The first one is saying that epsilon plus r is equals to r. Okay, so this means maybe in the last lecture of regular expression I have told you to denote it with this symbol, but this is also acceptable. Okay, so phi plus r is equals to r. That means if this is an empty set and this is a regular expression, the resultant is going to be a regular expression. The union of them. This is actually, so let's just revisit once more. This is the union sign. Whenever there are two multiplication, that means it is a concatenation. Okay, and whenever there is a star, that means there is a closure. Whenever there is a plus, that means there is a closure um, without the epsilon or null state. Okay. Okay, so let's continue to the next one. So the next one says that phi r plus r phi equals to phi. So that means the concatenation of a null set and regular expression is phi, and also the vice versa is true, and ultimately the union of these two phi's are going to lead into this phi. Okay. Epsilon r is equals to r epsilon and r. So you have to remember that phi means a set of null and epsilon means only a single null. Okay, that is what you are need to remember. So a single epsilon into r is equals to, so the concatenation of them is actually a regular expression. Okay, and the it is also commutative property is also applicable here. Now one thing you can see in the previous one, that here phi r plus r phi was producing phi, but here epsilon r is producing only r. The reason behind that is this is the total set. Okay, so if it is going to uh, gulp the regular expression into it, so it is going to again produce a null set. But here you can see that the regular expression is overpowering that particular one null expression. Okay, and it is finally combining all the concatenation of them are actually bringing up a regular expression. Okay, next up, the closure of a null is a null. Okay, and the closure of a phi is also a null. So that means either if it is a single null or a set of null, the closure of it is going to produce a null, always a single. R plus R equals to R. That means the union of two regular expression is going to be another regular expression. The concatenation of two regular expression and their closure is going to produce a single regular expressions closure. Okay. And it is also going to be true the next one, number 7, r star equals to r star r. Okay. There is no problem in it. That means a single regular expression and the mm, closure of a regular expression, their concatenation is equals to the vice versa thing, that is closure of a regular expression and the single regular expression. Next up is r star whole star. So that means a closure of a regular expression, and as a whole you are also closing the. So r star, that means a singular. Okay, you can see that r star is producing a singular. So obviously this is going to be r star. So closure of a single, the closure of a regular expression is going to be another regular expression. Okay, and if you put a whole of star, so it is going to be another r star. So this is no problem. Next one, epsilon plus r dash. Now you can see that this one is actually fetching this one. Okay, there is no problem. Now what is happening? This thing is actually r plus. Okay, that means if you don't recall this, please refer to my lecture on regular expression and regular language. Okay, in that particular lecture, you will find out this particular thing, that what is R plus and how it is coming. So R plus is basically a regular expression, a set of regular expression where null is missing. There is no phi. Okay, so uh, if we are union making an union of the epsilon with this r plus, actually what we are getting is r star. Okay, this is we already have seen in one of my previous lecture. So next up you have to remind these three also. Okay, so pq and whole star p is, so they are just reversing the whole thing, there is no problem. And also here you can see that the union of them is itself a regular expression, and if there is a closure outside, you can push the closure inside and it is going to work like that. Okay, so that is how it's work. And also here union and concatenation is little bit working like a plus and multiplication. Okay, okay, so let's carry on. So these identities are going to be required for whenever we are talking about further operations using regular expression. That's why this particular topic is very much important. So now, following the identities of the regular expression, we need to discuss one very important theorem that is related to the these identities. So this is called the Arden's theorem, which states that if P and Q are two regular expression over epsilon and over sigma, and if P does not contain epsilon, then the following equation in R is given by R equals to Q plus RP as a unique solution, that is R equals to QP star. Okay, okay. So how can I prove this? So I can prove this in two ways. Okay, let me just first of all. So this is the equation and this is the solution. So if I replace this solution in the equation, it should work. So first of all, let me just try. Okay. So R is equals to Q plus RP is given. So if I replace this R with QP star, what I am going to get? I am going to get QP star and Q. Okay. So if I take Q common from here, I am going to get epsilon plus P star Q. Okay. Now, if you look at the previous slide or go a few minutes back into the video, you will see that this thing, this particular thing is actually P star. Epsilon plus P star P is equals to epsilon plus P star is equals to P star. There is one identity like this. You can check in the identity slide. You can go back a few minutes. So I can write directly here. This is the QP star. Okay. So this is what I am getting ultimately. This is one way. Another way is to repeat the value of r again and again. So r equals to q plus rp. I hope this part was clear to everyone. This is one proof. You can prove it in two ways. This is one way, and now I'm trying the second way. Okay. Both are acceptable. So now I can replace it with the same value of this thing. Okay. So I'm going to get uh, q qp plus uh, rp square. Okay. Now again, if I replace this, I'm going to get qp square plus rpq. Okay. So like this, if I continue up to n, I'm going to get q plus qp plus qp square plus qpq, like this up to qp n plus r p n plus 1, because you can see when there was n, it was n plus 1 over here. Okay, so that is why I have applied that particular expression. So if I take now here, you can see that you can put this value of qp star over here. So this thing is going to continue, and here we are going to get, okay, let me just write this instead of, because this is an important part of this proof. So q plus qp plus qp square qpn plus qp star pn plus 1, right? I'll just replace the value of r with the value of qp star. Now if I take q common from here, I am going to get epsilon plus p plus p square, like this, pn, then p star pn plus 1. So if you look at the identities, you are going to see that this whole thing is actually the closure of this particular p set. Okay, so I can directly write this as qp star. So again, r is equals to qp star is getting proof. So both cases are acceptable. Okay, so let me just draw the clearer picture. Okay, so this is how. So you can either do this or you can do this. Both of them are acceptable. Okay. Okay. So now we have to understand how can I design a regular expression. Okay. So let's look at this example. Design a regular expression for the following languages over a comma b. So there are three cases given, where in the first case it is saying that it should accept a string of length exactly 2, minimum 2, and maximum 2. Okay. So how can I solve it? So first of all, you have to understand what are the language of acceptance for these three cases. So let's start with the first one. So for the first one, it is saying that it should be exactly 2. So what are the possibilities? It can be AA, it can be BB, it can be AB, and it can be again BA. Okay. So if I want to design a regular expression, it should be a union of all of them. So AA plus AB plus BB plus BA. Okay. So if I take A common from the first one, I'm going to get A plus B. If I take B common from the next one, I'm going to get A plus B. If I take A plus B common, I'm going to get A plus B. So that is the answer for the first one. For the next one, it says the string of length at least 2. So at least 2 means there is no maximum, but minimum is at least 2. So that means these 4 are going to be there. Apart from that, there can be millions and millions of possibilities. So this is actually an infinite set. So in that case, what I can do, I can uh, obviously these two are going to be there, A plus B and A plus B, and then I can put A plus B star, because whatever is the next following ones are actually the closure of this A plus B. So alternatively, you can say that whenever this case is becoming 3, so we can put uh, power equals to 1 over here. So in that case, it will be A plus B, A plus B, and A plus B. Whenever it is 4, I can put power equals to 2 over here, and it will be A plus B plus A plus B plus A plus B square. When we are talking about exactly 2, the power is actually 0. So that's why we are getting this A plus B into A plus B. So I hope this is clear for everyone. Next up, language accepting string of length at most 2. That means minimum can be anything starting from epsilon, and maximum shall be of length 2. Okay, so let me just make a union of them. So if you see, this first one is actually the important one. The rest of it you can find in exactly similar sequence of this one. So I can write this as epsilon plus A plus B into epsilon plus A plus B. Okay. So alternatively, you can say that if I want to find an epsilon, I can just multiply these two, epsilon and epsilon. If I want to find an A, I can just multiply epsilon into A. If I want to find B, I can just multiply epsilon into B. And for these three also, we are going to have this uh, the AA and AB and BA and BB. You can get all of this, right? Like this one. So this is pretty much easy. So I hope this has clear your concept for designing the regular expression. So this is the actual or clearer answer. Okay, so now we are going to discuss the designing of regular expression, or the using the NFA, or alternatively we can say that conversion of NFA into regular expression. That is the main objective of this current uh, problem statement. Okay, so let's take an NFA for example. Let's take this NFA. Okay, now why is this NFA? Because on same state, if you are applying one single input alphabet, it is producing multiple states. So for Q1 you can see that if we are applying A, it is going to Q2 and it is also giving a self loop. And also for Q2, if you apply B, it is giving a self loop and going back to Q1 also. Okay. So that is the reason, because as it is an NFA. Now we need to first of all write the equations concerned with this particular NFA. How can I write the equations? Actually, we have to just write the equations based on the incomings. Okay. For example, let's take the final state, that is Q3. So you can see Q3 has only one incoming, that is this particular one. All other things are outgoing. Okay. So we cannot take outgoing as a counter. We just have to take the incomings. So the incoming is Q2. Okay. So next up we have to uh, use the same thing for Q2. So for Q2 it is going to be the incomings are Q2B, the self loop. From Q1 we are getting Q1A, and from Q3 we are getting Q3B. For Q1 we are getting a self loop on Q1, and also we are getting an incoming from Q2. Okay, so that is Q1A plus Q2B. Now there is also one incoming from the beginning. Okay, so if there is nothing applied on that, that is basically an epsilon. Okay, so that is the null for this one. Okay, now we have to simplify these three equations to get our final regular expression. Okay, just follow me with this. First of all, let's try with the easier one, that is Q3. So what is the value of Q2? The value of Q2 is Q2B plus Q1A plus Q3B into A. So if I put the A inside, I am going to get Q2BA, Q1AA and Q3BA. So let's give these three equation number 1, equation number 2, equation number 3, and this one as equation number 4. Okay, let's take the equation number 2 for expansion. So in equation number 2 we had Q2 equals to Q2B plus Q1A plus Q3B. Now if I want to expand this or this, it is going to get more complicated. Instead I can expand this. So the value of Q3 from equation number 1, I can assume that this is Q2A. So here I am going to get Q2B plus Q1A plus Q2AB. Okay, so this is actually Q1A plus Q2. If I take it common, I'm going to get B plus AB. Okay, now if you look into this expression, it is going to look like the expression of the Arden theorem. Okay, you remember, if R is equals to Q plus RP, then the solution is R is equals to QP star. I hope all of you remember that from the last slide that we have discussed few minutes ago. So here you can say that this is my R, this is the whole thing is Q, and this is my R and this is my P. So the resultant is going to be Q1A into P is B plus AB whole of this star. Okay. So let's get this equation number 5. Now we have to take equation number 1. So equation number 1 was Q1 is equals to epsilon plus Q1A plus Q2B. Now I already have the value of Q2B, so just put it over there. Q1A plus Q1A B into B plus AB star. Okay, so I've just straight multiplied this thing with this B. Okay, so now if you look into this, you are going to find out that if I take again Q1 common, it is again going to look like the RP star thing, right? Sorry, Arden's theorem, that is R equals to Q plus RP, so R equals to QP star. So in this case, Q is basically epsilon and P is basically this thing inside the bracket. Okay. So what is going to be? So epsilon into P star, that means A plus AB into B plus AB star, the whole of this star. Also in the identities we have studied that if there is a epsilon multiplied with a regular expression, it is going to produce the regular expression. So remember that if R into epsilon is there, that is basically an R or R star, whatever you want to say. So that is basically A plus AB into B plus AB star whole star. Okay. Now what we have to do is we just need to put this value of equation 6 into equation 5. Then we are going to get an expression without any q1 or q2, and finally this value of q2 we have to put it in equation number 1. Okay, so in that way we are going to get an expression of q1, q2 and q3, which is not going to involve any state names, only the regular expressions. Okay, so I don't have any space left to write, but let me just try it. Okay, uh, which one is not required? Maybe this one is not going to be required at all. Okay, okay, let me just write it over here. So in this case we are going to have putting the value of equation 6 into equation number 5, we are going to get uh, q2 is equals to the whole thing that we got in equation number 6 into b plus ab star whole star into a b plus ab whole star. Okay, Now let's give this equation number 7. Now putting the value of equation number 7 into equation number 1, we are going to get Q3 is equals to this thing into A. Okay, so that is the final answer. So this one, this one, and this one, okay, are the final answers of the regular expression and conversion from NFA to regular expression. Okay, so let me just draw the clearer picture over here. Okay, so what we did just first of all we evaluated these three equations from the incomings for each of the states. Okay, then we expanded the easier one first, then the little bit more complex second, and lastly we expanded the much more complex one. So in this sequence we proceeded and we gave those equations another number 4, 5, 6. Now then we started solving from the much more complex one, as it has as it had no particular state in the right hand side, so it was only consisting the regular expression part. So now using this equation number 6, we put it into equation number 5 to get another state without a regular without any state in the right hand side, only the regular expression. Okay, so in that way we got the value of q1 first using a regular expression. We converted q2 next using a regular expression. Mm, okay, and finally we put the value of q2 into the equation of q3 to get the final equation. Okay, so that was the basic idea behind how to convert any NFA into regular expression. You write the equation, expand the equation until you are getting for any particular state you are getting uh, no state in the right hand side of that equation. Okay, you can use Arden's theorem or the identities or the properties of the regular expression. Okay, so now we are going to discuss one example where we are going to convert a DFA into a regular expression. Okay, so let's consider this DFA. The procedure is going to be same as we have seen for NFA. First of all, we have to write the equations. Okay, so here we have to look at the incomings for Q1, Q2, Q3, and Q4. So for Q1, the equation is going to be the only incoming we can see is Q2B. What else is there? Q3A is there. Is there anything else? Uh, I cannot see anything else. From Q2 it is coming, from Q3 it is coming. There is nothing else. For Q2, I can see there is only Q1A. For Q3, I can only see there is only Q1B. For Q4, there are plenty of them. So this is Q4A, Q4B, and also there is Q3B, and also Q2A is there. So now obviously we cannot start with this one because this is the most complex. We can not expand these two because it will get much more complex. I think it is wiser to start with this one as we already have the values of these two. So this give this equation number 1, 2, 3, 4. So let's start working with equation number 1. Put the values from equation number 2 and 3 and we are going to get q1 is equals to q1b plus sorry q1 ab and the value of q3 is q1b, so this is also q1ba, so this is finally becoming I forgot one thing, that there is a epsilon coming in over here, so there is an epsilon here. Okay, so there is an epsilon here. So before writing this, let me correct it first. There is an epsilon, then there is q1 into ab plus ba. Now this is again looking at the Arden's rule, r equals to q plus rp. So the solution must be r equals to qp star. So here q is epsilon and p is this thing. Okay. So this is going to be ab plus va star. Next, what do we have? We are going to have this. Uh, Now, as we have, obviously, this is the same. I have already explained this in the previous slide because the regular expression into epsilon is the regular expression itself. That is the value of q1. So let's give this equation number 5. Now put the value of equation number 5 into equation number 2 and 3. So we are going to get AB plus BA star into A, and Q3 will be AB plus BA star into B, and the value of Q4 is going to be Q4 equals to mm, Q4, take Q4 common, A plus B, and this is going to be mm, let's say Q3B and Q2A. Okay, so this is Q2A is going to be A into AB plus BA star A plus this thing is Q2A and this thing is Q2 Q3B. So Q3B is A, sorry, yeah, AB plus BA star into BB. Okay, so now you can see that this is again looking like an expression of the Arden's theorem. So you can convert it into QP star, where Q is this particular thing. This thing is Q and this is R into P. Okay. So here it is going to be QP star. So here it will be AA into AB plus BA star plus AB plus BA star into BB into this A plus B star. So this is the final answer, okay, for this particular conversion. So I hope this was clear to everyone. So this is the expression for Q4, for Q2, Q3 and Q1. These are the expressions, okay. So let me just erase all the inks, and this is the final answer. Obviously there is the expansion of Q4 is not done here. You can manually do it in your copies. Okay, so now we are going to discuss about the pumping lemma. So what is a pumping lemma? Pumping lemma is a tool. You can assume that it is a tool or a concept that is used to prove a language is not a regular. So far we have discussed about the regular expression, and also in one of my previous lecture I have discussed about the regular language. And what is not a regular language? That doesn't falls under the condition that is provided during the finite automata. So what are the conditions? That it cannot have a memory, it cannot store anything, okay. So uh, that is not regular language. So that in those cases, the languages that are accepted are regular languages. That are not accepted, which are going to require memory, is called a regular language. I gave an example of a to the power n, b to the power n as a not regular language, because yeah, we need to consider the values of n. That means if it is a cube, the next thing shall be must be b cube also. So these should be stored. So this is not a regular language. Okay. So now how can I prove it using pumping lemma? So the basic concept behind pumping lemma is that there are if A is a regular language, then A has a pumping length P, okay, such that any string S where S is greater than equals to P may be divided into three parts. S equals to X, Y, Z, such that the following condition must be true. Okay, so if these three conditions fail at the same time, then only you can say that it is not a regular language. If these three conditions are accepted, then you can say that it is a regular language. Okay. Okay. So that means arbitrarily, if any, you can consider this XYZ into anything. So that means whenever you are given a problem, you can divide it into three parts, and then you can start evaluating if these conditions are going to be true under the same rule. Okay. So if they are true at the same time, that means it is a regular language. If they are not same, then it is not a regular language. Okay. Now the basic concept behind pumping lemma is it is only used for uh, proving that language is not regular. It cannot be used to prove that language is regular. Okay, it can only establish that it is not regular. Vice versa is not true. So how can you do that? You need to provide or follow these steps. That assume A is a regular language. It has to have a pumping lemma of length. Let's say that P. Okay, all strings longer than P can be pumped. Okay. Now find a string that is in such that S is greater than equals to P. Okay. Now divide S into XYZ. So this can be anything, as I said. Show that XYZ for some I. So you need to consider all of the possibilities for I. Then consider always that S can be divided into XYZ. Okay, so you need to consider all of the possibilities, all of the permutation and combination. Lastly, you have to show that none of this can satisfy all the three pumping conditions at the same time. That means these three pumping conditions cannot be satisfied at the same time, or at least two of them, maybe one of them. Okay, and S cannot be pumped, so that is a contradiction. So this is still a vague concept. Let's take an example and that shall clear the concept. Okay, so let's take this example, uh, that proof that this particular language is not regular. Now, if you recall, I have just told why this is not a regular language, because you need to have a memory to store the value of n whenever a value of n is given. Okay, so that cannot be regular. But you know that you have to prove it using a bumping lemma, and these are the steps you have to follow. Okay, so first of all, let's say that A is regular. Okay, now it has to have a pumping length of say P. Okay, so let's say the value of P for this particular example is 7. Okay, now all strings longer than P can be pumped. So now let's say uh, the value of this thing will be A, 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 6, 7, and then B, 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 7 A's and 7 B. Okay. Now find a string is such that A's is greater than equals to B. Obviously it is greater than the 7. Divide A's into XYZ. Now I need to divide this thing into XYZ. Now there can be three possibilities. Possibility number one is where the value of Y is lying inside A. Okay. So let's say value of Y is inside A. So let's say the value of or length of Y is 4. Okay. So let's say this 4 is my Y. So this is my X and this thing is my Z. For condition number 2, let's say Y is in B part. Okay, so again, now remember this can be anything. I have taken length is equals to 7, doesn't mean you have to take 7 always. You can take anything, 3, 4, 5, 2, anything you can take. Okay, that is completely dependent on to you. The answer or the proof shall be same every time, but I'm just taking another approach. So again, 4 B's. So let's take these 4 B's. This is my Y. Let me just this. So this total thing is my X, and this is my Z. Okay. Another thing, another case can be Y is in X and A and B. So Y is in A and B. So in that case, again I have to write. Okay, so let's say this is the Y part, this is my X part, and let's say this is my Z part. Now we have all of this condition. Okay, I have divided in all ways of X, Y, Z. These are the possibilities. Okay, now I have to show that X, Y, Z belongs to A for some I. So here I have to check that what is the value of yi. So let's say I is equals to 2. Okay, so let's say I am evaluating for I equals to 2. So in that case, it is going to be x y square z. Okay, so if x y square z is there, the value of y will be doubled. Okay, so here it will be double a, and then 8 more a's, and then 6 7 b's. Okay, so this is x y square z. So is this belongs to a? So this is uh, the number of a is here is 8 plus 2, that is 10, and number of b is 7. So these two are not same, so that means it doesn't belong to a. Okay, for case number 2, this was case number 1. Now for case number 2, this thing will be same, a, but this thing will get doubled, and this thing will remain same. So again here the number of a is 7, and number of b is I don't know, 8 plus 2 plus 1, so that means around 11. So again this doesn't belong to set a, because the number of a's and number of b should be equal. Here if I double it, 5a was at the beginning. If I double it, then it will be 4 more a's and 4 more b's, and there is 5b later. So total it is going to be uh, 9a and 9b. So in this case it might get accepted, but in these two cases it is not getting accepted. Okay, so for some I, this is not acceptable. Okay, so if it is not acceptable, so that means condition number 1 has already fallen down from pumping lemon. Condition number 2 was uh, y must be greater than 0. So that is already true. Y is always 0. I have taken y, the length of y is 4. Condition number 3 was x and y is less than equals to p. Okay, less than equals to p. Now what is p? P I have taken as 7. So let's see if x and y, combination of x and y is always less than equals to 7 or not. So for the first case there were 6's. So for the first case it is acceptable. For the second case, the value of x and y together are 7 plus 4. So that is actually 7 plus 2 plus 4. So that is around 12. So for second case, it is not less than equals to 7. So this is not accepted. For the third case, 5 and 4 9 is not less than equals to 7. So that is not accepted. So that means condition number 3 has fallen, condition number 1 has fallen. That means ace cannot be pumped. Okay, So this is a contradiction. That means A is not a regular. So this is not a regular root. So let me just show you the actual solution. I hope this was clear to everyone. Okay. So this is the final solution. You can see that only for the first case it is getting uh, accepted, but in rest of the cases it is not getting accepted. So it is not condition number 1, condition number 2, and sorry, condition number 1 and condition number 3 has fallen. Condition number 2 was accepted, but it cannot be found since all three has to satisfy. Okay, so that was the proof. So remember, whenever you are given any expression, you can take the pumping length, anything, anything positive, but it is wiser to take something in the middle. Like 7, what I took was little bit far-fetched. You can see that sometimes I was missing some calculations. So it is moderate to use around 3 to 5, okay, for pumping length, and then proceed to the proof. And if you can check before starting that whether it is regular or not. If it and you can be sure that if it is not regular, then only you can proceed in the steps that you have been told. Okay, so that's it for today. Thank you for watching. Please stay safe, stay at home. From the next lecture, we are going to discuss about the grammars, regular grammars, CFG, and by the end of this week, we'll enter into the last module, Turing machine, and we'll soon finish the module inside 2 to 3 days to conclude our syllabus. Thank you. Catch you in the next one. Bye.